At the end of this topic, you will be able to compute the sum of n terms of an AP.
How many seats are there in an auditorium in which the front row has A seats, each row other than the front row has D more seats than the row in front of it? Schematically, the auditorium looks like the figure given in the picture. For convenience, let L denote the number of seats in the last or nth row. There are n rows. The front row has A seats. The last row has L seats. Let S be the total number of seats.
Now copy the diagram, turn it upside down, and place it next to the given diagram. The number of seats now amounts to the seats in 2 auditoriums. Thus, 2 copies of the auditorium produces a figure consisting of n rows, each having A plus L seats. If S is the sum of the seats in the auditorium, then 2S is equal to n into A plus L, which implies S is equal to n divided by 2 times A plus L. If the last row is the nth row, then L is equal to A plus n minus 1 into D, and the above formula becomes S is equal to n divided by 2 into A plus n minus 1 into D, which is equal to n divided by 2 into 2A plus n minus 1 into D. This gives the sum to n terms of an AP. Sometimes we are given an AP with only its first term and the nth term. How do we find its sum? Let us make matters simple. Call the nth term as the last term and denote it by L. Then the sequence can be written as shown. Now reversing the order and adding the terms, we get 2Sn is equal to A plus L n times. Thus, Sn is equal to n divided by 2 into A plus L. In other words, the sum of the first n terms is n times the average of the first and last term.
Let us see an example. Find the sum of the first 110 natural numbers. Click on the solution button to view the solution. Let us see another example. Find the sum of all positive integers less than 298 which are multiples of 9. Click on the solution button to view the solution.
Sum of the first 100 natural numbers. There is a story that when Gus was 10 years old and in the public school, his teacher, to keep the class occupied, set the pupils to add the numbers through 100. Almost immediately, Gus placed his slate on the annoyed teacher's desk. When all the slates were finally turned in, the amazed teacher found that Gus alone had the correct answer, 5,050, but with no accompanying calculation. Gus had mentally summed the arithmetic progression. He wrote the numbers and its reversed order and added them term by term. He got 101 plus 101 plus 101 and so on 100 times. That is 100 times 101. So the sum is 100 into 101. He has used each number twice. The answer would be 100 into 101 divided by 2, which is equal to 5,050. In this topic you have learnt, if the first term is A and the common difference is D, then the sum of n terms is given by Sn is equal to n divided by 2 into 2a plus n minus 1 into d. If L is the last term of a finite AP, or the nth term, then the sum of all terms of an AP is given by Sn is equal to n divided by 2 into A plus L. At the end of this topic, you will be able to compute the sum of n terms of a GP, compute the sum to infinity of an infinite geometric progression.
Sum to n terms of GP. Let Sn be the sum to n terms of a GP with first term A and common ratio R. Then Sn is equal to A plus AR plus AR squared plus AR cube and so on plus AR to the power n minus 2 plus AR to the power n minus 1. Equation 1. Multiplying both sides by R, we get Rsn is equal to AR plus AR squared plus AR cube and so on plus AR to the power n minus 1 plus AR to the power n. Equation 2. Subtracting equation 2 from equation 1, we get 1 minus R into Sn is equal to A into 1 minus R to the power n, which implies Sn is equal to A into 1 minus R to the power n by 1 minus R.
Let us now view the formula for the sum to n terms of a GP for some special cases. Case 1. Given R is equal to 1. When R is equal to 1, the sequence reduces to a constant sequence A, and so on, and Sn is equal to n into A. Case 2. Given R is less than 0. If R is less than 0, then Sn is equal to A into 1 minus R to the power n divided by 1 minus R. Case 3. Given R is equal to 0. If R is equal to 0, then Sn is equal to A. Case 4. Given R is greater than 0. If R is greater than 0, then Sn is equal to A into R to the power n minus 1 divided by R minus 1. Case 5. Given L, the last term, if L be the nth term, then L is equal to A into R to the power n minus 1, and so Sn is equal to A minus L divided by 1 minus R. This can also be written as Sn is equal to Lr minus A divided by R minus 1. Here is an example. Find the sum of the first 8 terms of 3, 6, 12, 24, and so on. To view the answer, click on the solution button. Now let us look at the next example. If S1, S2, S3 be the sum of n, 2n, 3n terms respectively of a GP, prove that S1 into S3 minus S2 is equal to S2 minus S1 the whole square. Click on the solution button to view it. Let us learn about infinite geometric progressions. We will consider the case when the modulus of R is less than 1. Consider the GP 1, 2 by 3, 4 by 9, 8 by 27, and so on. On calculating, we find that Sn is equal to 3 minus 3 into 2 by 3 to the power n. We observe that Sn becomes smaller and smaller and approaches 0 as n becomes larger and larger. Thus, if the modulus of R is less than 1, then R to the power n tends to 0 as n becomes larger. Sum to n terms. Infinite geometric progressions. For a GP with the first term a and common ratio r, the sum of n terms is Sn is equal to a into 1 minus r to the power n divided by 1 minus r, which is equal to a divided by 1 minus r minus a into r to the power n divided by 1 minus r. If the modulus of r is less than 1, then r to the power n tends to 0, and so a into r to the power n divided by 1 minus r tends to 0. Hence, Sn is equal to a divided by 1 minus r. Thus, the sum to infinity of a GP with the modulus of r less than 1 is given by S infinity is equal to a divided by 1 minus r, where S infinity denotes the sum to infinity. Let us now view an example on finding the sum to infinity of the geometric series. Find the sum to infinity of 4, 2, 1, and so on. To view the answer, click on the solution button. In this topic you have learnt, if the first term is a and the common ratio is r, then the sum of n terms is given by Sn is equal to a into 1 minus r to the power n divided by 1 minus r, or Sn is equal to a into r to the power n minus 1 divided by r minus 1. If L is the last term of a finite GP or the nth term, then the sum of all terms of the GP is given by Sn is equal to Lr minus a divided by r minus 1. The sum of infinity of a geometric progression is given by S infinity is equal to a divided by 1 minus r. Using the sum to infinity, we can find the rational number whose decimal expansion is given.
At the end of the topic, you will be able to calculate sum of first n natural numbers. Compute the sum of squares and cubes of first n natural numbers. Find the sum of some special series. Welcome to the topic on special series. Let us find the sum of first n natural numbers, that is 1 plus 2 plus 3 plus so on, plus n. The sum of natural numbers is given by Sn is equal to 1 plus 2 plus 3 and so on, plus n minus 2 plus n minus 1 plus n. Here, first term a is equal to 1 and last term L is equal to n. Therefore, sum of n terms is equal to n by 2 into a plus L, which is equal to n by 2 into 1 plus n. Therefore, Sn is equal to n into n plus 1 by 2.
Observe the following identity. X into x plus 1 into 2x plus 1 minus x minus 1 into x into 2x minus 1 is equal to 6x squared. Substitute the values of x as 1, 2, 3, etc. up to n minus 1 and n to get the equations as shown. Now let us add these equations. The like terms with opposite signs get cancelled. After all the cancellations, the term remaining on the LHS is n into n plus 1 into n plus 2. On the right hand side, we have 6 into 1 squared, 6 into 2 squared, 6 into 3 squared, 6 into 4 squared and so on up to 6 into n minus 1 squared and 6 into n squared. Taking 6 out as a common term, the RHS becomes 6 sigma n squared, From this we get the formula for the sigma n squared as n into n plus 1 into 2n plus 1 by 6.
Consider the identity x squared into x plus 1 the whole squared minus x minus 1 the whole squared into x squared, which is equal to 4x cubed. Substituting the values of x as 1, 2, 3, up to n minus 1 and n in the above identity, we get the equation as shown. Now, add these equations. The like terms with opposite signs get cancelled. After all the cancellations, we get n squared into n plus 1 the whole squared is equal to 4 into 1 cubed plus 2 cubed plus 3 cubed and so on plus n cubed, which is equal to 4 into sigma n cubed. Therefore, sigma n cubed is equal to n squared into n plus 1 the whole squared by 4, or n into n plus 1 by 2 the whole squared, or sigma n the whole squared. Now let us see how to find the sum of some special series. Find the sum to n terms of the series 1 into 3 plus 3 into 5 plus 5 into 7 and so on. Click on the solution button to view it.
Here is the list of formulae that we learnt in this topic for your reference.
Now let us see an example. Evaluate 51 plus 52 plus 53 plus 54 and so on plus 100. Click on the solution button to view it. Summation is the operation of combining a sequence of numbers using addition. The result of summation is their sum or total. If numbers are added sequentially from left to right, any intermediate result is a partial sum, prefix sum, or running total of the summation. The numbers to be summed may be integers, rational numbers, real numbers, or complex numbers. In this topic, you have learnt sum of the first n natural numbers is given by sigma n is equal to n into n plus 1 by 2. Sum of squares of first n natural numbers is given by sigma n squared is equal to n into n plus 1 into 2n plus 1 by 6. Sum of cubes of the first n natural numbers is given by sigma n cubed, which is equal to n into n plus 1 by 2, the whole squared, or sigma n the whole squared.